Right, second example. A machine makes bolts of diameter 0.58 centimetres. It's a mean, and we have the variance over here. After servicing, a random sample of 50 bolts is taken to see if the mean diameter has changed. Now here we go. Has changed. Not is greater, not is less than, has changed. That's going to be a two-tail test. It is assumed the standard deviation is still 0.015. The mean of the sample is 0.577. Test at the 1% significance level whether the mean has changed. So, if we go through the normal process, H0, the mean has not changed. H0 will be, the mean is 0.580 centimetres, the same as normal. The alternative hypothesis, it says it's changed. So that's saying mu is not 0.580 centimetres. So not equal to implies a two-tail test, and we'll see the implication of that in a minute. And we are dealing with this question at a 1% significance level. So, I would suggest, at least to start with, you do a sketch. It just shows you what's going on here. Under our null hypothesis, we've got a mean of 0.58. We've got a standard deviation of 0.015. A two-tail test, so I'm interested in tails on either side. Now this is symmetric, it's a normal distribution, and I want 1% overall in those shaded areas, which means I want 0.5% in this one, and I want 0.5% in that one. Together they make up my 1%. What's 0.5% as a decimal? 0.005. Yeah. Okay. So that is the area that there is in each of these tails. In that tail there, the area is 0.005. Right. D, they said, was normal 0.58, 0.015 squared. But we are looking at a mean, so we are interested now in the distribution of D bar. Josh, what will the distribution of D bar be?
Have a mean 0.58 and standard deviation 0.05 squared over n, which is 15.
Yeah, okay, that's the variance. Yeah, okay. That's taken from H0. That's the sample size. That's the sigma squared over n. And what we have to do is to find the critical region. So we need to find two values here then, C1 and C2. We're interested in it if it is in either tail. Now, it's already been pointed out before we started filming this one, we have a mean of 0.577, which is less than this, so we know it's not going to be over there. Okay, we are comparing with this one. So we need to find C1, because that is the side of the population mean that we are. So we want to find C1. If I put ST there, that's always going to be short for such that. Okay, such that, like we did in the last question. The probability that D bar is less than C1 is going to be that 5%. So it's a less than probability. So I'm going to write it down in phi's. It's my x value, which here is C1, minus my mean over standard deviation 0.005. The next step will be anti-phying. So over here on the right, I need to anti-phi 0.005. Just a quick recap, how do I anti-phi very small numbers? Use a graphics calculator or using the tables in the book, how do I anti-phi very small numbers? There's a 1 minus in here, but that's not enough in, and a negative over here, yeah. So I'm anti-phying 0.995 and sticking a minus sign in front of it. And again, 995 is in the tables, and it will actually be quicker in these to use the tables than the calculator, because these common ones will be in here. There's 995, 2576, 2.576. Stick a minus sign in front of it. And that is equal to what we had over here. This needs rearranging to find C1. If somebody can give us a shout in a minute, and if two people agree, we'll assume it's correct. It's our first offer. We agreeing then? Okay, that's correct. So I'm just going to do another diagram. You should have written right on the other one if you want. So I've got a critical value here of C1. I have my mean of 0.58. I have my critical value 2 there. How can I go and quickly find my critical value 2?
Would be the same distance from...
That's right, it's the same distance here. What is the distance between here and here?
0.58 minus 0.574.
And the answer to that? You don't need a calculator for that.
It makes it so much easier. 0.0055.
Yeah, so if we add 0.0055 onto that one, that must be C2 by symmetry. And the value we had was 0.577, which is here, 0.577. So we're not in a tail. If we were in either of these tails, we would reject H0, but our sample is not in either of those tails, so we accept H0. And H0 we wrote down as mu was equal to 0.580, and we need to end the answer with a sentence, so we would conclude that the mean diameter has not changed. Okay. This is still 0.580 centimetres. So our sample mean would have had to been even smaller than it was for us to conclude the process had actually changed. Okay. So for this one, there'd have been a... What will happen in this test 1 times out of 100? What will happen to our conclusion 1 time out of 100? Yeah, well, 1 time out of 100, even if it hasn't changed, we would get an answer in the tails. That's what the 1% significance level is. Because there's a 1% chance, because we have set these two probabilities here to 0.5%, there's a 1% chance that we will be in the tail even if nothing has changed. So there's a 1% chance that this test will be wrong. That's what the significance level is. 5% chance on the other one, 5% significance level, there's a 5% chance that we would state the wrong conclusion that way. So the lower the significance level, the smaller that percentage, the better. But there are pros and cons of making that small, and we look at that in the very final chapter of S2, chapter 7.